We're going to continue talking about problem-solving strategies. So this whole first chapter, like I've said before, is all about problem solving and different methods, approaches, strategies that you can use. And in this next section here, we're going to look at 3 more strategies. The first one touched on before. It's looking for a pattern. So this first example, we have 3 sequences of numbers, and we want to look for a pattern to fill in the next few blanks for each of them. Some of these are probably going to be a little simpler than others. So this first one here, we've done variations of this before. So we have 1, 3, 4, 7, 11. And if you just add the 2 preceding terms, you get the next term. So 1 and 3 make 4, 3 plus 4 make 7, 4 plus 7, 11, and so on. So you have 7 plus 11 make 18. Oops, there we go. And then 11 plus 18 are 29. And then 18 and 29 make 47. So in this case, the pattern is just by adding the preceding 2 terms. The next one, we have 2, 8, 32, 128. In this case, you're not adding at all, but rather you're multiplying. If you take each term and multiply it by 4, you'll get the next term. So 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. So just continue. 128 times 4 is 512. And again, multiplying by 4, you get 2,048. See if I can get it in there. And then your last term, again, multiplying by 4 is going to be 8,192. The third one is a little different once again. In this third one, you're not adding, you're not multiplying. There actually is a way that you can add with this third one, but probably the most straightforward way to see this third one is thinking of perfect squares. 1 squared is 1. 3 squared, 9. 5 squared, 25. 7 squared, 49. So it's our odd number perfect squares. So 1 squared, 3 squared, 5 squared, 7 squared. So following that pattern, the next one would be 9 squared, or 81. Then 11 squared, 121. And then the last one would be 13 squared, 169. So I mentioned a moment ago, that's probably the most straightforward way to do this one, but you actually can do this one with adding as well. You're adding consecutive multiples of 8. That's another way you could approach this one, though I'm going to guess most people are not going to see that right off the bat. Let me explain what I mean. 1 plus 8 is 9. 9 plus 16 is 25. 25 plus 24 is 49. 49 plus 32 is 81, and so on. That's another way that you could go about this one. Like I said, most people probably aren't going to see that pattern though. But the odd perfect square is much easier to see. Here's another one where we're going to be looking to extend a pattern. So here we have some equations. So 1 is just 0 plus 1, or 1 equals 1 is another way to just think of that one. Then 1 plus 3 plus 1 is the same as 1 plus 4. Then we have 1 plus 3 plus 5 plus 3 plus 1 is 4 plus 9. And we want to continue this pattern. So on the left side, I think that one might be the easier pattern to continue. We're going to do 1 plus 3 plus 5 plus 7, and then go back down, plus 5, plus 3, plus 1. So here we have odd numbers. And then the next one would go up to 9. 1 plus 3 plus 5 plus 7 plus 9, and then back down. So there we have the left side. The right-hand side, what's going on here? Well, before in part C, we were thinking of perfect squares, and we're going to continue with that. So I have, just looking at the right-hand side, I have 0 squared plus 1 squared. Then the next one down is 1 squared plus 2 squared. Next one down, 2 squared plus 3 squared. So if I continue that, I would have 3 squared plus 4 squared, which is the same thing as 9 plus 16. And then the following would be 4 squared plus 5 squared, or 16 plus 25. And you can double check. With this first one that's handwritten here, 9 plus 16 is 25. And if you add 1 plus 3 plus 5 plus 7 plus 5 plus 3 plus 1, if you add those together, you will get your 25. So there is our pattern there. The bottom of the page, I've just got a little blurb about Fibonacci. He has a very famous sequence where you're starting out with a 1 and a 1, and then it's adding those two terms to get your next term and continuing with that. It's just a famous type of sequence there. And you can read more about Fibonacci as you have time. But I want to do one more example here with another strategy. This is making a table. So we've talked a little bit before about making a table. Sometimes that's very helpful when you're looking for a pattern. So here we have a sequence of dots. So we start out with 1 dot, and then the next term in this sequence has 3 dots. Then we have 5 dots. Then we have got 7 dots. So the next one, we're going to end up with 9 dots, completing the pattern, and then 11 dots. So the 9 dots, we would draw it as 5 and then 4 on top. And then the 11, we've got 6 on the bottom. And 5 on top. So how many dots are in each figure? We've answered that one already. Then it says, how many dots would be in the 100th figure? So there's a couple ways that you could find this answer, and I'm actually going to show you something a little different here than what I have in my notes on BlazeView, just to show you there's 2 approaches to this. So this is my first term in the sequence, my second term, my third term, fourth term, fifth term, and sixth term. Now, notice that for each of these terms, to find the number of dots, I'm adding the term number plus the number 1 less than it. So let me explain this. The first term, there's 1 plus 0 dots, total of 1. The second term, there's 2 plus 1 dots for 3. The third term, 3 plus 2 dots, 5. Fourth term, 4 plus 3 dots, 7, and so on. Fifth term, 5 and 4 dots make 9. So for the 100th figure, if you're continuing that, there would be 100 plus 99 dots, or 199 dots in total. You could do the same thing for the 1 millionth figure. It would be 1 million plus one less than that, so 999,999, for a total of 1,999,999 dots.